Okay, so we have the third best paper, which is by William Pires, and it's a joint work with Chen, Mark Chen, Hao Kui, and Jonas Stockwell. It's about lower bounds for Boolean monotonicity testing.
Great, thank you for the introduction. Great, so in this talk, we're going to be interested in Boolean functions over the hypercube. Oh, okay, that was too zoomed in. Be good. And a function f is monotone if whenever you take 2 points, x and y, and x is below y in the ordering of the hypercube, you have that f of x is smaller than f of y. And that just means that if f of x is equal to 1, then you need f of y equal 1. So our goal in this problem is the following. We have some unknown function f, and we have query access to that function, and we want to use as few queries as possible to distinguish between two cases. Case 1, f is monotone, and case 2, f is far from monotone. So what does it mean to be far from monotone? So a function f is epsilon far from monotone if you need to change that function on at least an epsilon fraction of points to turn it into a monotone function. So instead of saying epsilon far for the rest of the talk, we're just going to fix a small constant epsilon in our head, and I will just say f is far from being monotone because we have this small epsilon in our heads. So with that in mind, our goal is the following. We want to use as few queries as possible, and if f is monotone, we want to accept with high probability, and if f is far from monotone, we want to reject with high probability. So there's been a super long line of work on this problem, and it all started in 1998 with this GGLRS paper. One thing I want to mention is people have not just looked at Boolean functions over the hypercube, they looked at different posets. They looked at real valued functions, but in this talk, I'll just focus on the Boolean case over the hypercube. So with that in mind, what's the upper bound that we know? So the first upper bound was by GGLRS, and it was the edge tester, which was an algorithm using n queries. 15 years later, this was improved by Chakrabarty and Seshadri, who gave the first tester with sublinear query complexity. Then this was improved by Chen, Savidio, and Tan, and eventually there was this result by Khot, Minzer, and Safra, who gave an algorithm that uses root n queries, and that's like the best algorithm that we know of. We don't know how to do better than root n. So how do these algorithms work? They kind of all work the same way, so you're just going to repeat the following a bunch of times. You create 2 points, x and y, where x is below y in the ordering of the hypercube, and if f of x is equal to 1, but f of y is equal to 0, you can reject because for sure your function is not monotone. And interestingly, all the testers that we know for this problem are non-adaptive. It means that the queries they make do not depend on the answer to previous queries. So you can imagine that the algorithm is making one enormous batch of queries, it receives the answer to all the queries, and then decides I accept, I reject. So it's something very parallel. And it turns out that for this kind of non-adaptive testers, root n is the best that you can do. So in this case, the KMS upper bound, which is root n, that's the best. And this follows from this sequence of lower bounds. So we know root n is the best for non-adaptive testers, but for a long time, it was not known what you can do if you have adaptive testers, so your queries can depend on the answer to previous queries. And in this work, we show that basically it does not help. So for any constant c, any adaptive tester, you need at least n to the 1/2 minus c queries. So what's important is that it almost matches with root n upper bound, and it improves the previous lower bound, which was n to the 1/3 by Chen, Waingarten, and Chen, which I'm going to talk a lot about later. So now I'm going to try to explain how we build these adaptive lower bounds, in particular how we build a family, a distribution of functions which are far from monotone, and give you a sense of why they're hard to test. So our work follows the one of Belov and Blaise and the one of Chen, Waingarten, and Chen. So one thing is we want to build functions that are constant far from being monotone. So for this, we're going to focus on the middle layers of the hypercube, which are points with Hamming weight n/2 plus or minus root n, because these layers have like a constant fraction of the points in the hypercube. So all the action in the lower bound is going to happen in like these layers of the hypercube. So for the rest of the talk, I'm going to ignore what's above and what's below in the hypercube, and I'm always going to use this hexagonal shape to represent the middle layers. So with that in mind, we're going to go to the Belov and Blaise lower bound, and the first ingredient we're going to need are the anti-dictator functions, which I'm always going to represent with this little sheep. And there's n anti-dictators. They're the function not x1, not x2, all the way to not xn. So these functions are far from monotone. They're anti-monotone. But if you have an adaptive tester, you can easily find that these functions are not monotone because you can do something like binary search using log n queries, and you'll find an anti-monotone edge. So the whole idea is that we're going to try to prevent the algorithm from doing something like binary search. Which leads me to the second ingredient, which is random Talleyrand partitions. So this is inspired by Talleyrand's random CNF. And so for this partition, we're going to draw 2 to the root n many terms, and each term is obtained by drawing root n variables independently and uniformly. And once you have this gigantic collection of terms, we're going to get a partition. So we are like looking at the middle layers, and so each gray region corresponds to points that satisfy a unique term. So the first gray region is points that only satisfy T1, the second one is points that only satisfy T2, so on and so forth. There's points that do not satisfy any term in white, and there's points that satisfy many terms in black, and we're going to ignore them because nothing's going to be happening with these points that's like super interesting. And these gray regions where points satisfy a unique term, they're going to be the cells of the partition. That's where all the action is going to be happening. So we're going to have 2 to the root n many cells, and with high probability, a constant fraction of points are going to fall into one of the cells. So now that we have our partition, for each cell, we're going to draw a uniformly random coordinate I, and we're going to set f of x equal not xi in that cell. So in the first cell, we're going to set f of x equal not x1. In the third cell, let's say we set f of x equal not x87. So after drawing our terms and our anti-dictator for each cell, we're going to get a distribution of functions which with high probability are far from monotone. And one thing is that, for example, if you have a point in one cell and a point in another cell, they are incomparable in the ordering of the hypercube, which means that like they're not telling you anything about each other as to whether or not the function is monotone. So now, if I'm a tester, let's say I have a point z that falls into one of the cells. This cell is defined by some term t, and inside that cell I set f of x is equal to not xi. How can I find that my function is actually not monotone? To do this, I need to find a point y which falls into the same cell, so y also satisfies this term t, but y and z disagree on this hidden coordinate I. And it turns out that this is going to be super hard because t is a random term, I is a random coordinate, so you kind of want y to be very far from z so that they disagree on this hidden coordinate. But if y is very far from z, then it's not going to be in that cell anymore, and so that's not useful. And the punchline is that indeed this is really hard and you need n to the 1/4 queries, and that was the Belov and Blaise lower bound. So after this, Chen, Waingarten, and Schier looked at this construction and thought, how can we make it harder? And the idea is that before we used like the CNF version, and now we're going to use the DNF version too. So we're going to draw 2 to the root n many terms, and for each term we're going to draw 2 to the root n many clauses. And again, each of these clauses is obtained by drawing root n variables independently and uniformly at random. And the punchline is that this gives you a more complicated partition. So the details of that partition do not matter so much, but roughly for each term, you're going to look at the points that only satisfy this term. And then using the clauses for that term, you're going to actually partition your points into little cells. And again, there's a lot of points that are not going to fall into any cells, but a constant fraction of points are going to land into one of the cells. And now we're going to do the same as before. For each cell, we draw a uniformly random coordinate, and we set f of x is equal to not xi in that cell. So that's why here you have like little different sheaps. It's because it's different anti-dictators that are drawn independently. So we have this more complicated partition, and guess what? We get a better lower bound. We get n to the 1/3. So that's great. We tried one level of partition. That was great. We tried 2 levels of partitions. That was even better. So surely 3 levels is going to be even better. So now to get 3 levels of partition, for each clause, you draw 2 to the root n many terms, and each term here is going to correspond to one of the cells in the partition, and in that cell, you plant a uniformly random anti-dictator. So that's why in each of these cells, you have like a little different sheep. It's independent anti-dictators. And it turns out that actually this does not help. There's an algorithm that still finds a violation using n to the 1/3 many queries, so this does not give you a better lower bound, which is perhaps a little surprising. So why is that the case? So I'm going to try to explain to you the algorithm that finds a violation using n to the 1/3 many queries. So the algorithm has like a really nice subroutine which allows you in n to the 1/3 many queries to build a set S, which is a subset of the coordinate which has 2 cool properties. So S is a large set, whatever large means, it's large. And S is going to be disjoint from a term and a clause below it. So you don't know what this term or this clause are, they're random. You just know that this set S is actually disjoint from them. And because S is disjoint from them, you can do cool things and play around with the coordinate in that set. And this allows you to start attacking the terms that are below this clause in the clauses, terms that you drew. And again, for that term, we have a little cell with like a uniformly random anti-dictator. And it turns out that here, if the coordinate that corresponds to this orange sheep is in S, the tester is going to find a violation to monotonicity super easily. So we basically lost the tester one, it can reject. So what's the tester going to do? It's going to try to attack many different terms. And because for each of these terms, we have a uniformly random anti-dictator, each time it attacks a term, there's like a 1/S probability that this anti-dictator is in S. And if that happens, the tester is going to reject with high probability. So that's great, and that's kind of what we were stuck with. So we looked at this algorithm for like a super long time, and what are we supposed to do to overcome this algorithm? And the idea is, perhaps surprisingly, is that you actually need a simpler distribution. So before, for each cell in the partition, you were drawing a uniformly random anti-dictator, and you were setting f of x equal not xi. What we do instead is we draw one anti-dictator at first, and we set f of x equal not xi for all the cells. So before you had like different little sheeps in all the cells, and now it's like the same sheep everywhere. And now if we look back at this algorithm, well, if the algorithm tries to attack many different cells, it's the same sheep everywhere. So that's completely useless, because now if that sheep is not in S, that's just not helpful at all. Again, the sheeps are the anti-dictators. And so the best thing the algorithm can do is just attack a single, and it's gone again. Oh God, okay. It's back. Too zoomed in, but it's back. So yeah, the best thing the algorithm can do now is just attack a single cell. And it turns out that now we can get a better lower bound, so we get an n to the 3/8 lower bound with 3 levels. But the cool thing is now we don't need to stop at 3 levels. We can use as many levels of partition as we want. So if you want to build L levels of partition, you do terms, clauses, terms, clauses, terms, clauses, as many as you want. And the more levels of partition you use, the closer you're going to get to an n to the 1/2 lower bound. So here in our theorem statement, like for any constant c, once you pick enough levels of partition, you can get this n to the 1/2 minus c lower bound. But there's a little bit of a catch, which is that the number of levels we're using must be a constant. Because as we use more and more levels, our cells are basically getting smaller and smaller, and we have less and less points in the cell, which means that like in the distribution of functions we get, the functions are going to be 100 to the minus L far from monotone, which is fine when L is a constant. 100 to the minus L is a small constant, but a constant. When L is not a constant, we run into problems. So shortly after this was fixed by Minzer, we used like our result as a black box and a distance amplification lemma, and he actually showed that there exists a constant epsilon, such that if you want to test between monotone or epsilon far from monotone, now you need n to the 1/2 minus of 1 queries. So that's stronger than our result. And the obvious question is like, is the right lower bound exactly root n or not? I think it would be really cool if it's not, because that would mean there's like some cool way of using adaptivity. And I think you would have to prove some really cool things about monotone functions if you want to do better than root n, even if it just helps a tiny little bit. And that's all. Thanks.
Any questions? Okay, so let me again ask a question. So do you think there is a gap between adaptive and non-adaptive, even logarithmic or anything like that? Right now it's exponent, it's polynomial.
That's a good question. I don't know. I feel like we don't know that much about monotone functions to like, maybe there's some really smart thing you can do using adaptivity. So maybe, I just don't know.
Mm-hmm. Is it possible actually that non-adaptivity is not helping at all?
Yeah, maybe adaptivity does not help at all. And again, that would be really, really cool, but we just couldn't get it with our construction.
Mm-hmm. Okay. Then let's thank the speaker again.